Hello, everyone, and welcome to the next lecture on reasoning based large language models. Today is the third lecture in our course, and we will continue the discussion on inference time compute scaling. Remember, in the previous lecture, we discussed about chain of thought reasoning and zero shot reasoning. Both of these are prompting techniques which are used to nudge the LLM to reason before the LLM provides an answer. Remember that in the chain of thought reasoning, we saw that for bigger models, the chain of thought reasoning performed much better compared to smaller models. And we saw this using a practical demo uh, on Google Colab as well. What did we see in zero shot reasoning? In zero shot chain of thought reasoning, we do not give any input output examples in the prompt. That is why it's called as zero shot. Instead of that, we simply nudge the LLM to reason by telling the LLM to think before it answers. It turns out that such a clever, nudging significantly outperforms plain zero shot reasoning without giving this statement which tells the LLM to think step by step. Both of these, remember, they are prompting techniques, which means that when the user is typing the prompt, that prompt is combined with either input output pairs of examples with a chain of thought or by a simple statement which says, let's think step by step. Today, we will understand about a second category of test time compute, which is called as search against verifiers. And this is going to be very different than plain prompting. So let's begin and let us understand what is the meaning of search against verifiers. So, verification means the process of generating different answers and then finally selecting best answer out of all the answers which have been generated. Uh, Now, verification, why are we even discussing about verification? Let's try to understand it with the help of the following diagram. So, in this diagram, what we see is that we ask a question at the top, and then the question gets passed to the reasoning model. And then what happens is that instead of providing one answer in the output, the reasoning model provides four different answers which are labeled as A1, A2, A3, and A4. Now, there is a verification layer in between which verifies which answer is the best out of the four answers, and then finally, the best answer is given. This is called as the verification layer, and we are going to learn exactly about this layer in today's lecture. So, let's look at a very simple analogy. Imagine that you are given a task of, selecting the best quality crop in a field. And let's say the field is huge, and you start by surveying the field one by one. You find a crop, you pluck it out, and you see that, okay, this is a really good crop. Do you stop at that? No, right? Generally, what we do is that we pluck more and more crops, and then we select the best crop out of maybe five or six that we have sampled. That way, the probability of getting the best crop increases. That is exactly the case with large language models also. Instead of generating a direct answer, what is usually done is that there are a sample of answers which are generated, and then with the help of the verification layer, the best answer out of the samples is chosen, and then that answer is shown back to the user. Now, let's go back to the title of this lecture, Inference Time Compute Scaling. How does this fit under this title? Well, remember that if we have a verification layer, we talked about test time compute in the first and second lecture. When you have a verification layer, it's going to increase the computational resources which the LLM uses during inference. That is why it comes under inference time compute scaling, because the inference time is going to increase. Uh, let's look at it in the form of a diagram. Whenever you are using an LLM, there is a pre-training, then there is fine tuning, and then there is inference. So without verification, inference is like this. But when you increase verification, you are basically increasing the time which the LLM takes to give you the answer, because you are sampling from different answers and you're selecting the best answer. That's why it increases the inference time compute. Now, this verification layer that we looked at, it can either be done by humans or it can be done by a model. The models who do this verification are called as reward models. Why don't you go to Hugging Face and type this reward model? It's called reward model Deberta V3 large V2. What it says is that this reward model is trained to predict which generated answer is better judged by a human given a question. So it's used for model evaluation, reward score in RLHF, and detect potential toxic responses via ranking. So this model is trained such that if you give an input to this model, it will give you a score based on how good the generated answer is. So the training data that this model has been trained on was generated by humans itself. And then that data is being used to train the model. So we are essentially mimicking the ability of humans to verify answers by replacing humans with a model. Okay, so these are called as reward models because uh, the best answer is rewarded with the maximum score. If the answer is not good, then the score will be less and the reward will be less. In the next section, we are going to look at reward models in detail. So, more specifically, there are two types of reward models. There are outcome reward models and there are process reward models. And the purpose of both these type of models are pretty much, explained in their names. So let's look at the first category, which is the outcome reward model. So imagine that you have a question and you pass this question to a reasoning model. So the reasoning model is going to give you a chain of thought. It's going to give you the thought process through which it thinks before it gives you the answer. Now, what the outcome reward models do is that they don't evaluate these thoughts. They don't care about the thoughts basically. They only care about the final answer and only the final outcome is scored. So here ORM represents the outcome reward model and point 45 is the score which the ORM gives to the final answer. The next category which are more popular are process reward models. And these make more sense because when you are using a reasoning model, the thought process is very important for you. So there needs to be a mechanism which judges not just the final answer, but also the individual thoughts which are leading to the final answer. So here what you see is that thought 1 is sent to the process reward model and then the model is scoring the thought. Thought 2 is again sent to the process reward model and the model is again scoring the thought. So here the main difference compared to the ORM is that individual reasoning steps are scored and the final answer is not scored. So you are assuming that if the reasoning steps are correct, obviously the final answer will also be correct. So you are giving a lot of emphasis on the chain of thoughts which are leading to the final answer. That is why it is called as a process reward model. So now let us look at a practical example of a process reward model, and how does a process reward model work in practice. So let's take a simple example. Let's say the example which we are considering is Roger has five tennis balls and he buys two more cans of tennis balls. Each can has three tennis balls. How many tennis balls does he have now? So, like we saw in the last lecture, we are going to use a chain of thought reasoning to come up with the final answer. So, we have three steps. Step one is the reasoning LLM says Roger started with five balls. Step two is two cans of three tennis balls, each is five tennis balls. And step three is so the total number of tennis balls is 5 plus 6, which is 11. Now, read these and just try to understand which one is a correct and which one is not correct. The first one is correct. Roger starts with five tennis balls, so you get a higher score. The second one, two cans of three tennis balls, should be totally six tennis balls, not five. So this one gets a lower score, see. And then, so the total number of tennis balls, the final answer is correct. So this one gets a higher score. So wrong reasoning gets a lower reward. The main advantage of using verifiers is basically there is no need to fine tune or retrain the LLM which you are using to answer the question. So, whenever we are working with reasoning models, whichever reasoning models you see in practice, whether it's O1, DeepSeek, etc., it is likely that these reasoning models, before they give you an answer, a verification layer has been added where there is a process reward model that is evaluating the answers and it is giving you the answer which has the best possible reasoning path. Okay, so now let's move ahead and we will look at the different types of verifiers. Broadly speaking, we will look at three different types of verifiers. We'll look at majority voting as the first type of verifier. Then we will look at best of n. And then finally, we will look at beam search. All of these are very intuitive and simple to understand, but we are going to have a look at these three types in detail so that you understand the intuition behind them. Okay, so the first one, let's look at it. The first type of verifier is called as majority voting. And before we go ahead, I want all of you to download this paper, which I have enjoyed thoroughly. There might be some aspects of this paper which you do not understand, but I hope this paper will. If you have gone through the first three lectures, I hope you will understand some aspects of this paper and really appreciate this paper because this paper specifically discusses about test time compute. So you will be able to understand the theory which has been outlined in this paper. Okay, so after you have downloaded this paper, we will start to now discuss about the three main types of verifiers. The first verifier is called as majority voting, and this is clearly the most intuitive. In majority voting, what happens is that there is not even a verifier used actually. What happens is, let's say you probe an LLM to generate samples of answers. Let's say there are 10 answers generated by the LLM, and you pick the answer which appears maximum number of times. That's all. So something similar to this. Let's say you ask the question, are the number of prime numbers finite? And then you give it to the reasoning model, and the reasoning model generates six chains of thoughts which you are not concerned about at all. You just look at the final answer. Okay, so you can see that there are two yeses, but there are four no's. So what's the majority? The majority is no. So we will choose the majority in this case, and the final answer we will pick as no. So this method is also called as self consistency, but this is probably the first thing which came to the mind when people thought of verifiers, that let's sample a lot of answers and pick the answer which comes uh, the maximum number of times. Okay, so this is the first answer, and now here, mind you, the main drawback of this method is that the the answer can be wrong because you are not using any verifier to evaluate the answer. So there is no way to know whether the answer is correct or not, but you are simply taking the majority, and that concern is actually addressed in the next method, which is called as best of n samples. So here again, what happens is that there are n samples which are generated by the LLM, but the difference from the previous method is that you apply a verification layer here. You don't directly choose the majority, but you apply a verification layer, and then you choose the answer which the verifier is giving the maximum score to. And this can either be done by a output reward model or a process reward model. So let us look at both these examples now at the bottom. So the question that we have asked is, how many moons does Jupiter have? It is passed through a reasoning model, and then we have generated six chains of thoughts: T1, T2, T3, T4, T5, T6. So as we are looking at ORM here, we are not concerned with the chains of thoughts at all. We are only concerned with the final answer. These final answers, which are 90, 1, 95, 82, 76, and 14, they are passed through the output reward models. And then this verifier scores all these answers: zero point 0.6, zero point 0.2, zero point 0.9, 0.7, 0.3, 0.5, and then you pick the answer with the best score. So the number of moons in Jupiter which Jupiter has is 95. By using the ORM, this is the answer we get. Now, when you look at PRM, in PRM, what we do is we don't score the final answer like we do in the previous step. But let's imagine that this is a question, and we pass this question through to the reasoning model. And here we are evaluating three chains of thoughts, which are T1, T2, and T3. Okay, so T1 goes down to T11, T2 goes down to T21, and T3 goes down to T31. Both these reasoning steps are passed through the PRM, and we are getting scores zero point 0.1 and zero point 0.2, and we are doing a weighted average. So it is 0.15. Here again we are doing an average which is zero point 0.6, and here we are doing an average which is 0.55. And now we are not even bothered about the final answer which the reasoning model is giving, because the verification layer only verifies the reasoning steps which are appearing before the final answer. So from these three, we can see that this answer has the maximum score. So that's why we will pick this answer. So the answer with the best average is finally selected as the final answer. Okay, so this is using PRM for best of n sampling. And then you can also imagine an example for this which looks very similar to the above example. But the primary motive behind showing you both these methods is to understand the differences between the two. And you can see in this paper also, which I have shared before. In this paper, they have predominantly focused on process reward models, and these models are more effective, and they are more frequently used in practice by researchers. Okay, now we will go to the next algorithm or next verifier in this case, which is using the technique of, or we can call it verification using the algorithm of beam search. So the beam search algorithm was originally proposed in the year 1976, and it was proposed in this paper, which is shown below. The title of the paper is The Harpy Speech Recognition System, and this paper actually came out in the year 1976. Uh, so, this algorithm was first used in the speech recognition domain. And here you can see that the search strategy, the name of the search strategy is a few best paths in parallel. So this is quite an ancient algorithm, we can say. It is not an algorithm which is developed by LLM researchers or AI researchers. It was developed way back, around 50 years back, we can say, where the name was not even given as beam search, but the algorithm was very similar to the modern algorithm. And it was used for speech recognition tasks. So, Beam search continued to be used for speech recognition and translation tasks in subsequent years. It was a popular algorithm. You can even go to Wikipedia and search about it. You can see that the references date back to earlier years. So, why are we discussing beam search in this course of reasoning models, and particularly how can we construct an effective verifier using the algorithm of beam search? So let's look at that in detail. So first, we will understand how the traditional beam search algorithm works, and so that your intuition is developed, and then we will apply that algorithm to construct a verifier which is very effective. And then finally, we will run a hands-on a Google Colab notebook, which will give you a practical understanding of how beam search is used in actual LLMs for verification layer. Okay, so we will take a very simple example, which is a sentence in Hindi. So the sentence says that मैं दिल्ली जा रहा हूँ. This is a sentence in Hindi which translates to English as I am going to Delhi. And this is the task that I want to do. And now I'm going to explain to you about beam search algorithm specifically applied to this task. So, firstly, we have this text corpus, which is, let's say, around 50,000 words. And we can only use these words in the translation tasks. We can we cannot use any other word when we are translating this sentence from Hindi to English. Okay. So the approach that we are going to take is, uh, we are going to translate this sentence word by word. So now let's look at it. Step zero is we are given a text corpus, a list of 10,000 words, or we can even call it, say, 50,000 words. And we have to use only the words in the text corpus for the translation task. Now, the next step is, out of these 50,000 words, we will select the most probable three words for the first word in the translated sentence. So, if we go through all these words, we have selected I, we have selected Delhi, and we have selected zoo. We have eliminated all other words. You might ask the question, how are these selections made? These selections are made via an encoder decoder model, but we are not concerned about how these selections are made right now. Imagine that there is a model which is making this selection. We are going to understand about the beam search strategy. This model can be anything, it can be a black box for all we know. So we pass this text corpus to the model and we select the three words which have the maximum probability. That is step number one. So these words are I, Delhi, and zoo. Now the interesting thing comes in step number two. In step number two, what we do is we pass these three words again through the entire corpus, and now we find the next three combinations of two words which have the maximum probability. So Now how many combinations we have to see? Let's say 10,000 plus 10,000 plus 10,000. So now we have to sorry, this is 50,000. 50,000 plus 50,000 plus 50,000. Out of 1,50,000 combinations, we have to choose the best three combinations of the first two words. So you can see here that we have eliminated I was, we have eliminated Delhi is, we have eliminated all others, and we have selected only three. Again, we have selected I am, we have selected I love, and we have selected zoo is. Remember that in the first step we passed 50,000 words. In the second step, we are searching across 1,50,000 entries. And then we are again choosing the three most probable entries by passing it through the model, which is a black box for all we know right now. So step number two is, for each of these words, we will select the most probable combination of first word and second word and select the best three. So these are I am, I love, and zoo is. Okay, so now one thing you can immediately notice from this is that there is no Delhi here, so you can actually completely eliminate this Delhi. So that reduces uh, the chances of first word from three to only two. That is, the first word can either be I or zoo, it cannot be Delhi. Okay, now in the next step, what we do is we again pass these combinations of three to 50,000, 50,000, and 50,000. So again, we evaluate across 1,50,000 combinations. And now we choose the next best possible three, which can be, let's say, I am going. So these, after this here, we again have to pick three. So let's say I am going, I love Delhi, and zoo is green. We select these. Or let's not, or third one is I love zoo. So now you can see here that zoo is not coming anywhere first, so this means that we can eliminate zoo, and now we fix our first word, which is I, and then this process will continue till we have translated the entire sentence. So beam search is essentially a technique. So now here, you can see that why did we select three? At every step we were saying let's select three, let's select three. Three is called as the beam width. So instead of selecting just one, we are selecting three in each layer. Then we are proceeding ahead. Then again we are selecting three in the next layer, etc. So three in this case is called as the beam width. And I think the name beam search came because it's like, imagine there is a huge library and you are shining a torch in that library, and there is a beam which is created through that torch shining, and that beam falls on three books or three letters or three words. So here I think it's like that, right? It's like it branches into three. So from a huge corpus, it branches into three. Then again, it branches into three. So probably it widens your search scope, and that's why it's called as beam search. But this is the exact algorithm which was used in the original paper, which came out in 1976, and subsequently it has been a popular model in speech recognition tasks. Now, for us and for this course, we are going to look at uh, how beam search can be combined with a reasoning large language model and a reward model to search many different reasoning paths and come up with an optimum answer. So in this case, we searched across many different words, right? But here, when we are looking at reasoning models, we are going to use beam search to explore multiple reasoning paths before we come to the final answer. I hope the intuition is clear for all of you. And with this intuition in mind, now we are going to move towards understanding the beam search algorithm, and how can we develop a verifier which uses a beam search algorithm to effectively search across multiple reasoning paths. Okay, so now there are basically two parameters here that we are going to look at. The first parameter is the number of beams, and the second parameter is the beam width. Okay, so there are two parameters which we are going to look at in this example. The number of beams we are going to fix as 4, and the beam width we are going to fix as 2. So let's understand now how we construct our uh, reasoning paths using the beam search algorithm. Now, because the total number of beams we have set to 4, in the first step, what the model will do is that the model will uh, the model will generate four different thoughts, which are given here: one, two, three, and 4. Okay, so in the first step, the model has generated four different thoughts. Now, what we'll do is, out of these four thoughts, only two will be selected. Why two will be selected? Because the beam width is 2. Remember how in the previous example also we selected 3 in each layer? Exactly with the same intuition, we are going to select 2 in each layer. So these two are, marked in green here. So we are going to eliminate thought number 1 and thought number 3, and we are going to only choose thought number 2 and thought number 4. The purple background here is the verifier. So it is because it has gone through a process, a reward model, that it has scored each of these steps. Maybe this step, this thought got 0.15, this thought got zero point 0.8, this one got zero point 0.3, and this one got zero point 0.7. So that's why we choose the best two. This is the first layer. Now what we'll do is, from both of these, we'll select two each. So in the next layer, we'll have 2 into 2, that is 4. In each layer, we need to have four different thoughts because the number of beams are 4. So now what we'll do, from each of these, we'll select two more. So in the first layer, we had 4, and now in the second layer also we have 4. 1, 2, 3, 4. From this, we have branched 1 and 2. From this again, we have 1 and 2. Okay, so this part is clear. And then again the process repeats. Out of these four, because the beam width is 2, we'll select the best two. So probably this got a score of zero point 0.9, this one 0.1, zero point 0.2, and zero point 0.7. So after the verifier has scored them, we can see that 1 and 4 have the maximum score. So we'll select 1 and 4. And the process continues. So finally, you get a diagram which looks like this. So here the question is, Roger has 5 tennis balls. He buys 2 more cans of tennis balls, and each can has 3 tennis balls. How many tennis balls does he have now? And this is the first layer, this is the second layer, this is the third layer, and this is the fourth layer. You can see that in the first layer, we have selected 2. In the second layer, out of 4, we have selected 2. In the third layer, again, we have selected 2. And in the last layer, we have selected 1, which is the final solution, which is the full solution. It's marked in the complete. So the color is complete inside. It's not an empty color, which indicates intermediate solution. So this is the diagram where number of beams are 4 and the beam width is equal to 2. Because the beam width is equal to 2, we only selected 2 at each step. So this is how beam search allows us to, effectively search all the reasoning paths. We are not just, scoring each reasoning path and then taking the average. Now this is a bit advanced. What we are doing is that we are selecting the best at each, and then we are completely neglecting others. Then from there we are again branching out, and we have and this kind of beam search technique, when applied in the reasoning models, it is shown to increase the accuracy of the answers. Okay, so this is how beam search can be used to explore multiple reasoning paths and then finally come up with the best answer. And now, in the next step, we are going to look at a hands-on implementation of beam search with process reward models. Again, all of these are process reward models because we are scoring each step. We are not just scoring the final answer. So that's why we have employed process reward models in this methodology. Okay, now what we are going to do is that we are going to write a code which gives us a beam search tree like this, and we are going to give an exactly same prompt which we have given over here. And then you can see that in this layer there are four. Again, in this layer there are four and four, because the number of beams are four and the beam width are two. So we are choosing two in each, this two, this two, and this two. And the two that we are choosing in each layer, let's look at this layer. So we are choosing the thoughts which have the maximum PRM score. So here you can see that green and yellow form lie somewhere here, whereas purple lies somewhere at the bottom. So the model does not choose that. The model only chooses thoughts which has the maximum color. And I'm going to show you a Google Colab notebook which I have written, which can give you a beam search tree like this. I will share this link in the chat. Again, I have used a A100 GPU here to run this code, since I have a Google Colab Pro subscription. And these are the different steps which I'm going to explain to you right now. The first step is to install the dependencies, and here we are also installing this graph viz, because we want to plot this final graph at the end, and because of that we are installing networkx and matplotlib.pyplot as well. Then after that, what we do is we load our reasoning model. We are using this Zephyr 7 billion parameter reasoning model for our case. And you can refer back to the code which we saw in the last lecture, where we had this exact same block of code. So now this block of code repeats whenever you are loading your reasoning model. The block of code remains the same. And now we are loading our process reward model. I am using this process reward model here, which if you copy paste you will see it's hosted on Hugging Face. So this is the process reward model I'm using for this Google Colab notebook, which is called reward model Deberta V3 large V2. So this is the reward model which has been trained from human feedback. It can also be used for toxic response detection and some other tasks as well. Okay, after the process model has been loaded, we are now using the ORM. This is called ORM here, but actually it's PRM. So we are converting this ORM to calculate scores for individual steps. So we need to write a piece of code which performs stepwise scoring. So that's why we call this function as stepwise PRM score. And then this particular block of code is used for this particular block of code is used to actually write the beam search algorithm. So here I have the same notation. I have n for the total number of beams, and I have m for the beam width, and the maximum steps, which are the different layers, are three here. And this is what is shown here. Because it's three, we have only one, two, and three. We don't go below that. You can play around with these parameters and see how the graph changes as well. Okay, so this is how the graph is plotted. And then finally, for visualizing the beam search tree, we define a function called plot trace graph tree clean. And then this is where we enter our prompt. Roger has 5 tennis balls. He buys 2 cans of 3 tennis balls each. How many tennis balls does he have now? So here, you can see the scores which the reward model gives for different beams. So you can see that here we do not have much variation in the answers actually. So all of these beams are giving the same answer, which is 11, which is the correct answer. One of the techniques which they have mentioned in the paper is that if you change the temperature of the model, you get different variations in the answers, and that allows you to explore the answer space much better. So here we are not doing any kind of exploration as such, because we are not varying the temperature variable, uh, and also because probably our model size is also smaller, that we are not able to see that effect clearly. So the temperature we have set to zero point 0.9, which is pretty high. Initially I had set it to zero point 0.7, but then I increased it because I wanted to see the variation in the answers which are given by these different beams. So you can see that we have a final beam 1 answer, we have beam 2 answer, we have beam 3 answer, and we have beam 4 answer. And then all of these are actually same. So here we are not able to see that difference essentially, but you can see exactly how the beam search code can be written along with a reward model to score the reasoning steps, and then select the best to move to the next layer, select the best to again move to the next layer, and then select the final answer. So I encourage you to try out different plots, different prompts, different number of beams, beam width, and then play around with this code a little bit, and also try to see what kind of variations we can do to get different answers in whenever you are looking at these final answers. Now another thing I want to highlight is that the paper which I was mentioning before. uh, okay, so they mention, so the way that paper is written is that you will, so this is the paper I am talking about. In this paper, they divide the paper into two categories. One category is, of course, verifiers, which you will be able to understand after going through this lecture properly. The second category which they mention is modifying proposal distribution. So verifiers is where you have a verification layer which grades your answers. But proposal distribution is modifying the answers which are generated in the first place. So what comes under proposal distribution is chain of thought reasoning, which is few shot, as well as zero shot chain of thought reasoning. These are examples of strategies, prompting strategies, which can modify the proposal distribution. So you can essentially look at these two methods as, this is the sampling method, which samples different answers or generates different answers, and this is the method which grades different answers. So whenever you are using this technique of building a reasoning model by leveraging inference time compute scaling, then you can either modify proposal distribution or you can implement a verification layer inside. Both of these are viable techniques. In the previous lecture, we looked at how you can modify the proposal distribution by prompt strategies, which is chain of thought prompting and zero shot chain of thought prompting. And then the second method is implementing a verifier along with the reasoning model. So the verifier can be using beam search, majority voting, or best of n. Any of the three options can be used. Okay, so this brings us to the end of the lecture. I expect all of you to implement this Google Colab notebook, and I expect all of you to download and start reading this paper also. This paper will uh, strengthen your knowledge of inference time compute scaling, and it will act as an effective culmination of the first three lectures that we have seen so far. The next lecture, we will start with some items such as tree of thought reasoning and Monte Carlo search. We will look at both these techniques very briefly, and then we will start with the next method of building reasoning models, which is learning about reinforcement learning, and we'll start learning RL from the complete basics. Please let me know in the comments if you have any doubts, if you are following this course so far, because that really gives us a lot of encouragement to push ahead and to keep going with these lectures. Thank you very much, everyone. Bye.